So we are indeed into lesson number 6, week 6 of the course. And this week we're returning back to the topic of thermochronology, as we will be in the final 2 weeks of the course here. Let me just take a look. So nothing seems to be significant based on the comments that I'm seeing here for our... Okay, exercises were kind of hard, but I managed to do them. That's good to hear. Yeah, I mean, this was a little bit different exercise, and as I mentioned, I think even during the exercise session on Friday, that this was a topic that I was not sure whether I would keep in the course this time around, but decided to keep it in just because there are a handful of interesting problems that come up with the exercise, like having to deal with certain situations where equations do or do not apply nicely. So as you saw, for example, in problem number 1, when we looked at positions that were in the negative y values compared to where this glacier valley was, so things that were basically on the left side of the plot, you saw weird behavior for even exponents, and we had to come up with a trick to solve that problem. So that was kind of one example, plus just rearranging the equations to solve for certain terms. That's something we hadn't really done much in the previous exercises, so that was the reason I kept that around. But it's good that you managed to do the exercise, and you know, if you're still having problems with the exercise, maybe let me know in Slack, and I can try to give some help there. But yeah, that seems like maybe that covers the extent of issues from week 5, and obviously we don't necessarily have a representative sample of participants in the course today, but still that pretty much covers us. So then, yeah, we can go here to our materials for lesson number 6, and what you can see here in our overview for this week is that we have a couple sets of lecture slides, so we'll go through those to basically probably for the first half of the time that we're here today, and then there's a link here for exercise exercise number 6, and exercise 6 is not yet ready. That'll be posted later today, so sorry about that, but I can give you an overview of the idea of exercise 6, and then we can talk about the final paper description, because yes, there is a final kind of paper that you'll write based on exercises 6 and 7, and we'll go over that at the end of the course time today, so at the end of today's lesson. But yeah, why don't we get started here? If there aren't any questions at the moment, or if there are, maybe you can post something in the chat. Otherwise, I'm going to get our slides up here for the first lesson piece today, where we're going to talk about low temperature thermochronology, and I'm just going to hide my zoom controls so I can see this better. And yeah, we've already talked a little bit about thermochronology earlier. We introduced, I think, already back in week 3, the basic idea. When we talked about diffusion, we talked about Dodson's equation and the idea that we can date minerals based on their temperature and their kind of temperature history. So the idea being that we can get the time since the mineral was either open and losing all of its daughter product it would produce from radioactive decay, or really what we're dating is the time when it becomes a closed system and starts trapping that daughter product, and the accumulation of the daughter isotopes would then give us some age that we can interpret, and that's our thermochronology idea. Hopefully that sounds familiar. If not, you can go back and have a look at the materials from lesson number 3, and maybe remind yourself of the basic ideas of thermochronology. But today what we're going to talk about is low temperature thermochronology. So conceptually, this isn't really different from other kinds of thermochronology. It just applies to low temperatures, and really what that means is we're going to be introduced to a couple different low temperature thermochronometers. So these are different dating methods that are used. The reason for introducing this has to do with what we'll do in exercises 6, 7, and the final paper. So you might benefit from knowing a little bit of the background here on helium dating, on well, not so much on fission track dating, but I'll introduce it anyway because it's a very common low temperature thermochronometer. And then on argon dating, which is not necessarily low temperature, but still we'll see it in exercises, well, at least in the final paper, and I think actually maybe in exercise 7 as well. So the idea here when we say what is a low temperature thermochronometer is basically all we're doing is referring to thermochronometers that have a closure temperature or an effective closure temperature below about 300 degrees Celsius. So as you'll recall, that closure temperature is the sort of temperature at which the mineral starts trapping the daughter isotopes inside of it. So that was the idea with the closure temperature concept that we introduced back when we were talking about Dodson's method for calculating an effective closure temperature. And what that means for us is if we look here at a plot of different thermochronometers, I think we saw this same plot back in, it may have been week 3 already. There are different types of thermochronometers. They're based on different daughter products being produced. So they're argon-based systems where argon is the daughter isotope. There's these uranium, thorium, helium systems where helium is the daughter isotope. And then there's fission track systems where, well, we'll talk about that a little bit, but essentially a damage trail inside the mineral is the daughter product. It's not a daughter isotope in this case. And what you can see is that most of the fission track systems and uranium, thorium, helium systems, at least on this plot, this is by no means a complete list of different thermochronometers, but most of these fall below closure temperatures of, of 300 degrees, which means that they are these kind of low temperature systems we're interested in. We're also going to talk about using muscovite with the argon-argon system, so that's a little bit higher temperature, but that's, we'll come to that. Why is this useful? Why do we care about distinguishing low temperature thermochronometers from other kinds of thermochronometers? Well, there are a few reasons. One of them is that, just like any thermochronometer, the history that we have and that's recorded in the age is essentially the history of some rock being brought from depth up toward the Earth's surface, usually by erosion if we're using this like in a mountainous setting. But here you can see also that this is an extensional fault in this little cartoon here. So there would be exposure that's also driven by tectonic activity. By this fault slipping down, you're exposing rock that was covered by the hanging wall before, and that rock would then also be exhumed. So it's basically, we're bringing rocks up to the surface in two different ways in this case. But basically, in the picture that you can see here, where this rock sample comes up to the surface, these little dashed lines in here are showing kind of a trajectory from some depth up toward the Earth's surface. So where it reaches the surface and where it kind of passes through this effective closure temperature here, I think it's like 60 degrees is used in the example diagram here, will depend on where you are at the surface. So if you're close to the fault here, you might have a short distance that you travel between the closure temperature and the surface, whereas if you're up at the top of the mountain here, it might be a much longer distance. And that'll be reflected in the age being different for those different cooling histories or those different kind of cooling pathways. So with the low temperature systems, we're usually looking at depths to this closure temperature that are somewhere between 1 and maybe up to 15 kilometers depth, and ages that are on the order of 1 to maybe hundreds of millions of years. And so what this means is that we're somewhat sensitive to what's happening in the upper crust, happening near the Earth's surface, and we can calculate things like long-term average rates of tectonic activity, for instance, with this fault slipping here, or erosion over this time scales of 1 to hundreds of millions of years. So the idea is that compared to a lot of other methods we could use to try to study how things like mountainous landscapes evolve, this low temperature thermochronology as one of the ways that we can directly look at things like rates of erosion over long time scales. And what's unique about the low temperature thermochronology systems in particular is that they're very sensitive in a way to what's happening with things like the topography and the erosion and tectonic processes, because they pass through this closure temperature fairly close to the Earth's surface. So that means in this case here that you can see even from these temperature lines that are drawn in here. So these different temperature lines are isotherms, so lines of constant temperature. And you can see that this 45 degrees C, the 60 degrees C, and the 75 are all sort of bent upward here beneath this mountainous sort of high topography here. And then they're bending down here where you have a basin that is sort of having sediment deposited into it. And this is somewhat mimicking the geometry of the surface topography, but not exactly. So you can see that here you've got sort of low, flat elevations, and then it curves upward for the mountains, and the sort of temperature contours, these iso lines of constant temperature, follow that same pattern. So they're actually being affected by the shape of the topography. And that makes sense in a way, because essentially what we're looking at the surface is a temperature boundary between the atmosphere and the solid rock. And then the rocks underneath that are going to be affected by, for instance, colder temperatures up here at higher elevations, and relatively warmer temperatures down at lower elevations. And also the shape of that top surface will then affect those lines of constant temperature. So that's what's really useful in this case, is that we can study things like how the Earth's surface topography has changed over time, in addition to rates of erosion and rates of tectonic movement of faults. So just to say a little bit about the same kind of idea, I won't go through this in a lot of detail. You'll have the slides on the course page if you're interested to look these over in more detail. But basically, if we go to a sufficiently high temperature and we imagine that we have some kind of fake topography here, so this is our sort of fake mountainous landscape in like a profile, kind of like a cross-section view, where we have a mountain here and a valley here. If we go to high enough temperatures in the Earth, the temperatures at depth are not affected by the shape of this topography. So as you can imagine, once you go more than maybe 10 or 20 kilometers below the Earth's surface, the variations in the elevation of the Earth's surface are no longer really affecting the shape of these lines of constant temperature at depth. So if we go deep enough and high enough temperatures, essentially the lines of constant temperature are at a constant depth relative to, for instance, sea level. What that means is that if you were to look at things like, do I have it here? Yeah. So if you looked at how long it takes for a rock to move from this depth up to the surface in a mountain compared to this depth up to the surface in a valley, you see that there's a difference in the length of these two pathways. And so you would expect it would take longer to reach the surface at a mountain peak than it would at a valley. And in fact, we see this when we look at these thermochronometer ages. If we look at them compared to the elevation at which rock is collected, you'll often see that there's a relationship here between the age being older at higher elevations. And there's a little bit of scatter because there are other things that could affect the age, but essentially this is a commonly observed phenomena in mountainous landscapes where people have done this thermochronology dating method. So this relationship of older ages at higher elevations is something kind of interesting. And yeah, there is, here kind of no topography sensitivity. Well, that's not quite exactly this, accurate. There is still a sort of relationship between elevation and the ages, but things get different when you start looking at low temperature thermochronometers. So like we saw in that cartoon at the beginning, when we move closer to the Earth's surface, these lines of constant temperature, so for instance, your closure temperature isotherms, will be affected by the surface topography. So you can see we have the same topography we had before, but now we're at a shallower depth, and this line of constant temperature for the closure temperature here is now bent following a sort of damped version of that surface topography. The effect is that you still may have some relationship here where you're getting older ages at higher elevations, but the length of these two arrows could be closer to similar to one another, so that age relationship might not be as clear as it was in the higher temperature systems. But you can see that now the topography is affecting the closure temperature isotherm here in the curved dashed line. And what's really interesting is so there's a little bit of a change in the pathway, getting longer in one case, shorter in the other, and that's why these ages have kind of rotated to having a steeper slope. But what's really interesting is that it takes time to conduct heat through the Earth's crust through geological materials, and if the time scale over which things like the topography are changing occurs during the time that the rocks have passed through the closure temperature on their way up to the surface, you can end up with a very interesting relationship here. And the point is, and don't worry about the details necessarily, but we had a higher mountain here that's now at a lower elevation. We had a deeper valley that's now been filled in to some extent, and the change in the sort of length of this pathway now has ended up that it's actually a shorter pathway to the surface here where we used to have a mountain, and a longer pathway where this valley has been filled in. And you can even end up with this weird relationship where your ages are actually younger at higher elevation and older at lower elevation, which means that there's a way to actually reconstruct an old topography using this method. And that's what is one of the sort of interests or areas of interest in using low temperature thermochronology, is that you can really study past topography, which is not something easy to do by very many other methods. So if this doesn't totally make sense to you, don't worry about it. We don't need this for the exercise, but it's just to kind of give you a sense of why people are using low temperature thermochronology. So let's jump back here to our list of common thermochronometers. You can see that there are these three kind of classes or groups. These are all the same kind of like isotopic system, but used in different minerals. So now what we're going to do is go through some of these different systems and how they work, just briefly, so you have some idea of how the dating method works in case you're interested from a kind of geological perspective. You maybe learn a little bit about how these like systematics are actually working in more detail than we've seen so far, which could again be useful for the final paper in the course. And we'll start here with this uranium, thorium, helium method. So this is what's kind of generally referred to as helium dating. And the basic idea is that we're going to use the accumulation of helium-4 from parent isotopes of uranium-238 and 235, thorium-232, and samarium-147. So if you have these isotopes present in your target mineral, then their radioactive decay will generate helium-4 from alpha decay. And the alpha decay that occurs will result in this daughter isotope possibly being trapped within the crystal, and then you can date your mineral using that. And these, 238 and 235 uranium, thorium-232, and samarium-147 are relatively common in minerals like apatite and zircon, which is why this method is often used on those minerals. Over here on the left, you've got kind of like a decay chain. This is the production of alpha particles by decay, and what you can see if you follow the little pathways here is that if you start with uranium-238, every time you have one of these diagonal lines like this, you produce an alpha particle, and if you follow along its pathway to its ultimate lead isotope where it ends up at the end, you'll see 238 uranium produces 8 alpha decays, 235 uranium 7 alpha decays, thorium-232 is 6, and then samarium 147 is 1 alpha decay. So that's why it's not listed up here as like uranium, thorium. It's sometimes listed as samarium here, but it's not as much of a source of helium as the others. So sometimes it's even excluded in the name of the method. But that's the basic idea. These are all radioactive parent isotopes, and they produce helium by alpha decay. And here's the kind of age equation if you wanted to calculate it. You don't necessarily need this, but in case you're curious as to know like how is the age or the kind of production of helium calculated, in this case, we know that there's 8 alpha decays, so then we just say 8 times the decay of uranium, or the concentration of uranium-238, and then multiplied by some factor that's related to its decay constants. And so you can see in each case here there's an e to the decay constant times t term that will determine how much helium is produced. And again, you don't need this for the exercise, just for some background information. In practice, when people go and do use this method for dating, they're going to be looking at things like apatite crystals. So these are some apatite crystals in sort of a view through a microscope. And you can see here, I think this is about 100 microns scale bar. So you can see these are sort of like 100 to 200 micron apatites. These are nice datable apatites here because they still have their sort of prismatic shape. They still look like the crystal, whereas the not so nice ones are kind of beat up and not looking very much like a crystal. But this dating method really relies on being able to find fairly pristine looking crystals in order for it to work properly, and there's a reason for that. But basically we're going to select the crystals here, degas them, and measure the amount of helium that's inside them using a mass spectrometer. That's the idea with the dating method. Why does the shape matter? Well, it matters because it's possible that some of these alpha particles, when they're produced, can be ejected. So if you have a uranium, 238, right near the edge of your crystal in your apatite, the alpha particle, when it's produced, will be traveling some distance, like about 20 microns from where it's created. And so, these little circles here would all indicate, if there's an alpha decay, where that alpha particle could possibly go, anywhere in the sort of like it would be like a spherical volume around the point where the alpha decay occurs. And as you can see, if you're near the edge of the crystal, it's possible the alpha particle just gets ejected out of the crystal, and then you don't ever have that helium, even though the decay occurred. So we can compensate for this, but it really relies then on being able to have crystals that are close to the shape that we would expect for a nice prismatic apatite, for example. And then there's even a sort of note here that yes, it's also possible to have implantation. So if you have another apatite right next to this one and there's alpha decay there, it could possibly travel, that the alpha particle travels into the crystal even though the decay occurred outside. So this can be accounted for if we know the geometry of the crystal fairly well. So I think that's the kind of just very quick overview of how this uranium, thorium, helium method is working, just so you have some background knowledge for the final paper, as I mentioned. And I guess if you have any questions, you can maybe put them in the chat as we go along. But again, this is just kind of background information that might be useful to know for the final paper in the course. And if I don't see any questions, I think I'll move on here to just say a little bit about fission track dating. It's a different kind of method, and it's not something we'll use directly in the final paper, so I won't say as much about this. But it is a very common low temperature thermochronometer based on these fission track systems. So I think it's worth at least mentioning a bit. And the basic idea here with fission track dating is that we are going to date a mineral based on a damage trail that's created from spontaneous fission of uranium-238. So fission, in contrast to the kind of alpha decay that we saw earlier, results in essentially splitting this atom in half. And so now we have a much larger, you can look at the atomic mass, for instance. Before we had an alpha particle with a mass of 4. And now if we take 238 and divide it by 2 roughly, we're going to end up with two pretty big isotopes that are going to propel themselves apart from one another, repel each other. And as they repel apart from one another, they're going to leave a damage trail through the crystal. And those damage trails can be carefully enlarged and made visible so that we can see them under a microscope, and then we can simply calculate the density of these damage trails to come up with an age for this method. So this is something that's been done for a little bit longer than the helium-based methods, because essentially you could do this under a microscope with less need for an extremely precise mass spectrometer, which is one thing that the sort of uranium, thorium, helium dating needs. So when this spontaneous fission occurs, we produce these damage trails. They're about 16 microns in length in apatite, about 11 microns in zircon. And they do behave somewhat similarly to a typical thermochronometer, in the sense that once you've produced one of these damage trails, if you're at high enough temperatures, the crystal will heal itself, basically. It will anneal the damage that's been done there and repair this damage trail such that you don't see it. So at high temperatures, that annealing process occurs. At low temperatures, the annealing process does not occur, and so the damage trail is left there, which means, again, we have this kind of temperature sensitivity that can be used for dating as a thermochronometer. And so you can see here on the left some examples of these damage trails in I think apatite in this case, and these have all been enlarged after etching with some strong acids for a certain amount of time. So yeah, as mentioned here, in order to see these damage trails, we have to basically enlarge them to see them under a microscope, and that's done by basically immersing the sample, a kind of cut surface of the sample with some acid, and then that makes these acid flow into these tracks and enlarge them. And then they're able to be counted either by hand, or there are some methods now that are being used for automatic calculating of these damage trails to get an age. And then here we have, again, an age equation that's based on the number of spontaneous tracks that have been formed. So that's NS here, and some decay constants and things like that. And you can come up then with an age using the density of these fission tracks. And you can see, for instance, here, this is a polished mineral surface. So this would be like, if you cut your sample and then polished a nice clean surface, that there are tracks that are going to intersect that surface. Those tracks are not necessarily ideal, because they're going to be then partially shortened by having cut this surface, but they can serve as pathways for acid to travel into tracks that are deeper within the crystal, these confined tracks, and those are what are more useful, because then you can see the full length of the track. These are still good to give us some sense of the density, but obviously near the surface there's possible problems that could arise. If you polish your surface more, you'll change the number of tracks you might see, for instance. But the confined tracks here that can be generated by either cleavage or a sort of host track that allows acid to flow into these others, those are the ones that are typically more appealing. So as I mentioned, it's just a very quick introduction to the fission track dating method, just so you kind of know how it's working, but it's not in the exercise this week, so we don't need to worry about that too much. The other method I want to just say a few words about is argon dating. So 4039 argon dating. It's based on the decay of potassium 40 to argon 40. And obviously, for those with the geology background, you'll know that potassium is one of the more common more common and most abundant elements in the crust. And so that means that this kind of production of argon 40 from potassium 40 is something that happens commonly in many different upper crustal rock types. So this is a sort of appealing target in a sense because it's so common that you can find minerals, potassium feldspar and various micas with potassium in them that make it a good source for dating with argon dating methods. So yeah, as mentioned here, white micas, biotite, K feldspar, and amphiboles all are target minerals for argon dating. So this works somewhat similarly in a way to the uranium, thorium, helium dating, because argon is also something that is kind of not going to incorporate itself into the crystal lattice, but rather be one of these noble gases that's just going to be trapped inside the crystal, just like helium. And the ages are found by irradiating a sample with fast neutrons. So this will produce argon 39 from potassium 39. And then you can calculate a ratio of argon 40 to argon 39. And that's done either by kind of total fusion of the sample. So that's essentially where you just release all the gas by heating the sample up and measure the amount of released argon 40, or step heating, which is where you sort of heat up to a certain temperature and then see how much argon has been released, and then heat it further to a higher temperature, and again measure whether there's been more argon released. And you'll see how that works on the next slide. Again, we have an age equation that's related to the amount of argon 40 and argon 39 that are measured, and then there's an irradiation factor here, J, and I don't really know the details of how the method works beyond this, so we'll leave it maybe at that for the moment. But the step heating idea is that this is a way in which we can find out whether our mineral has cooled quickly or cooled slowly. The reason for this is that if a mineral containing potassium 40 has cooled very quickly, the concentration, for instance, in that mineral of argon 40 will be pretty much constant across the width of the crystal. And what this means is that as you do this kind of step heating, where you gradually increase the temperature and see how much argon is released, you'll see that this amount of argon being released is pretty much constant as the temperature is increased. And the reason for that is that if you start out with lower temperatures, you're only going to release argon from the edges of the crystal. So here we have like one rim on the left side and one rim on the right side, and this is our concentration of argon that's constant across the crystal. At the beginning, in this case, the concentration's high near the rim of the crystal, and so at low temperatures, when you first start to release the helium, the whole crystal hasn't been heated. It's only kind of heating the outside, and then you get, even the whole crystal could be heated. You're only getting the sort of transport of argon from the edges of the crystal to being released out to the outside. As you heat up more and more, you'll get more argon coming from further toward the center of the crystal. But in this case, because the concentration's constant, you see that the argon release and the argon age is pretty much constant as well. This is in contrast to a kind of a slowly cooled mineral, where what you would expect is that during this slow cooling, you're going to be losing argon near the edges of the crystal as it's cooling down geologically. And that argon loss near the edge of the crystal, because remember that it will still be diffusing out toward the edges of the crystal over time. The argon loss that you see there will result in the behavior that when you start heating the crystal, there's very low concentration at the edge, and you see almost no argon released. And as you heat it to higher and higher temperatures, you start to get more of the argon toward the center of the crystal, and you'll see the kind of increase in the amount of argon being released as you heat up more and more. So you'll end up here with like something that we might call like a plateau age, which is actually then maybe giving you a more meaningful idea of what the age of this crystal actually is based on the amount of argon that has been calculated, or that has been accumulating inside the crystal as it's been cooling. So this distribution of the amount of argon over time, or as a function of how much you've heated up the crystal, is really useful to be able to tell the difference between rapid cooling and slow cooling, because otherwise you only know how much argon has accumulated, and you might come up with a conclusion that these ages are very different because you've lost a lot of argon during slow cooling here, and here you have sort of a constant amount of argon. So you can come to different conclusions based on these cooling histories that you have here. And so this step heating method is very useful in that sense to distinguish slow from rapid cooling. And the same kind of step heating could be used for the helium dating method as well. We just didn't really talk about that, but it's been more well established for argon dating. This last slide on the argon dating is, well, we don't need to worry about this in too much detail, but the point is that you can end up with these different apparent ages. So like we saw before, if we have a constant concentration, so that's our example A here, we expect to see a constant amount of argon 39 that's released when we heat up our sample. And that's no big surprise. If we've had a slow cooling, then this is where we see maybe less argon released at the beginning, and then it increases as you go to higher and higher temperatures with this step heating. But it is occasionally observed as well that you start up heating and you release a bunch of argon, and the amount of argon you release over time is decreasing, which would suggest that the concentration of argon at the edge of the crystal is actually higher than it is in the middle. And this is a slightly unexpected behavior. Makes it quite difficult to interpret your ages, but there's essentially excess argon, and this is like the term that's often used in describing this problem when it's encountered, that can sometimes be taken up from other minerals that are right next to your target mineral. So if there's something that's producing a bunch of argon, it's possible that you could end up with argon, sort of like excess argon near the rims of your crystal. And then again, with the step heating, what you want to do is you sort of release that excess argon, and you hope then that this age that you reach here, this apparent age plateau, gives you some meaningful information about what the age of the crystal actually is. So yeah, this then kind of takes us back here to our overview of these different thermochronometer systems. So the uranium, thorium, helium system, we saw mostly examples from apatite, but it's commonly applied in zircon as well as titanite, although that's not as common as apatite or zircon. We saw the fission track system, and again, apatite is probably the most common target for fission track dating, although zircon is also, again, very popular. Systematics of fission decay and things like that are perhaps a bit better known in apatite. But zircon usually has a lot more of the radiogenic parent isotopes present in the crystal, so it's appealing in that sense. And it's also a very durable mineral, so it's can withstand a bit of being beat up by nature and still be able to be used for a date. And then finally, the argon systems that we just talked about can be used in potassium feldspars. It's a little bit tricky. We won't go into the details, but there's some challenges dealing with feldspars. White micas are probably one of the more common target minerals, like muscovite, for argon dating, and biotite can be used as well, but excess argon is a bit more of an issue with biotite. And then if you're going to higher temperatures, you can of course use hornblends. So we can skip the recap here, I think, and I'll just remind you the reason that we've introduced this is that the final two exercises are based on thermochronology. We've already seen this in exercises, exercise 3 notably. And the sort of exercise 6 is broken up into two pieces. So what you do in week 7 will be based in part on what you've already started doing in week 6. And as usual, you're going to do this kind of modification of a Jupyter notebook to make some plots and answer some questions. And then the questions you answer for these exercises, particularly in exercise number 7, will be relatively simple. So maybe not as much work as the sort of earlier exercises because they're going to be related to this final written report that you will produce for the course. So for the written report, we'll go through this in a bit more detail in a few, well, after our next set of slides. But the basic idea is that you can either use a Jupyter notebook, so provide a template for this, or create a Word document that's something like 6 to 8 typed pages, single-spaced and including figures. So this might seem like a lot of text, 6 to 8 pages single-spaced, but you're going to probably have 3 or 4 figures in there, and you'll lose quite a bit of space just from those alone. And the figures are going to be things you can take directly out of exercises 6 and 7. So that's the kind of handy part of how this all comes together. So you're going to have in this report the opportunity to provide a little bit of background on the data you're going to use, and I'll give you some details about that data and things like that in the exercise and in the description of the final paper. And you'll also be able to describe the methodology that you're using and what kind of results you have from the code that you've run. And the style of the report is sort of like a formal written report. It's kind of like a journal article in a sense, in that you'll have like an introduction, a background, something about your methods, some results, a discussion, and then some conclusions. And this will be basically just pulling information out of what you've already done in exercises 6 and 7. But of course, there's some background material that you'll need to bring in as well. And we'll talk about this in a little bit more detail, as I mentioned, but just to kind of give you the idea of how these things are fitting together. Okay, so that was low temperature thermochronology pretty quickly. I'm just going to turn off my notifications. Are there any questions at this point?
When is the report gonna be due?
So I think the tentative due date for that is like 12th of January. So, we can talk about this as a group in terms of like what would fit your guys' schedule. But the point is, I don't want you to have to work on this over the Christmas break. So something like 12th of January would mean that you would have part of the week after the course ends, and then like a week or so before teaching starts in January. So that would be hopefully okay. But yeah, we can talk about it if you're concerned about the schedule for that. Any other questions at this point? Okay, well, if not, why don't we take 5 minutes break and we can come back about 10 after 9, and then we'll continue. I'll introduce exercises 6 and 7, then we can go over the final paper in a little bit more detail, and if other questions come to mind, then you can ask those at that point. But yeah, let's take a 5-minute break and come back at about 10 after 9.